Okay, here's problem 350 in the problem solving videos, and it says find V0 using nodal analysis. And we're going to rely on the problem solving strategy on page 102 on nodal analysis. You'll note here that we only have current sources, no voltage sources, and if you'll note, we have a dependent current source in this problem. So let's start off identifying our nodes. 1, 2, 3, 4. That whole thing on the bottom is a node. Let's pick the bottom node as a reference. So in our circuit, we have 4 nodes. We picked one as a reference. That gives us 3 node voltages. And those node voltages, let's label them on the diagram as V1, V2, and V0. So then we'll have V1, V2, V0, and then that means we're going to have to write 3 equations. Okay, so let's start off applying KCL at the nodes corresponding to V1, V2, and V0. So let's start over with the node on the left, and when we write this, we're going to write it and not worry about the IA to begin with. We're going to go ahead and write it as if it were known. Then we'll go in and substitute in IA and eliminate it. So again, let's sum currents leaving through resistances and set it equal to currents entering from sources. So for this node, we'll have V1 over 3K plus V1 minus V2 over 6K. And then we'll have 2IA entering and 0.002 amps leaving. Okay, so there's our equation, and we see where IA is. Okay, so IA is here, and if we note, then IA is V2 minus V0 over 2K. So now if we want to go ahead and substitute this in, we can do that now to eliminate the this variable. So we have V1 over 3K plus V1 minus V2 over 6K is 2 times V2 minus V0 over 2K minus 0.002. Okay, so there's our equation, and now we need to rearrange some terms in this equation. So let's do that. So we'll have, for instance, 1 over 3K plus 1 over 6K times V1. That collects those two terms, minus 1 over 6K times V2. And then let's move this term over on the other side. So we'll have minus 2 times V2 minus V0 over 2K is equal to minus 0.002. And if we continue with this, you can see that we're going to get a minus V2 over 1K, and then we're going to get a V0 over 1K. So again, just simplifying our equation sum, we have 1 over 3K plus 1 over 6K V1. Then we'll have plus quantity minus 1 over 6K minus 1 over 1K times V2 plus V0 over 1K is equal to minus 0.002. So there's our first equation. Okay. So now we still need to get 2 other equations, okay, at the other 2 nodes. Okay, and now we need to apply KCL at this node, and then at this node. So again, we'll sum currents leaving through resistances and set it equal to sum of currents entering from sources. So for the middle node, we'll have V2 minus V1 over 6K, then V2 over 6K, that'll be that current, and then we'll have V2 minus V0 over 2K, and that's equal to 0. So if we simplify that, we'll have minus 1 over 6K V1 plus 1 over 6K plus 1 over 6K plus 1 over 2K times V2 minus 1 over 2K times V0 equal to 0. So there's our second equation. Now we need one more equation, and we'll get that by applying KCL over at the node on the right. And again, we sum currents leaving through resistances, set it equal to sum of currents entering from sources. We'll have V0 over 1K plus V0 minus V2 over 2K is equal to 0.002. And if we simplify that, we'll have minus 1 over 2K V2 plus 1 over 1K plus 1 over 2K times V0 is equal to 0.002. So there's our third equation. Now, for the solution, let's solve using Matlab. Let's write our equations in matrix form and then solve them using Matlab. Okay, so in matrix form, our equations would become the following. And then here's the next equation. And then here's the third equation. Now, we solve those using Matlab. Then we get V1 is minus 8.5714. V2 is minus 1.1429. And V0 is 0.9524 volts. And there's our answer.